Wait. This is not a cooking video, I promise. This is a video about our paper, Cloud Scale Runtime Verification of Serverless Applications. And this is joint work with Panda, Leonid, and Muli. We all share the goal of correct software. This is especially true for serverless applications. We've known for a while now that serverless is a double-edged sword. On the one hand, serverless platforms have some very useful features that drive adoption and make programming and deploying cloud applications easy and, dare I say it, fun. On the other hand, these same properties of serverless applications restrict the developer's visibility into the inner workings of the application. They make monitoring and tracking the application behavior hard, and they make debugging a running application a serious challenge. But it turns out that serverless is actually a triple-edged sword. So, on the other hand, some of these same serverless features allow you to build scalable and efficient runtime verification mechanisms. In this talk, I'll show a few of the challenges that serverless poses, the solutions to those challenges that serverless provides, and the runtime verification system, called Watchtower, that we have designed. So, you've written a serverless application. What does that mean? Well, some event occurs in the real world, and your application code needs to run. You don't have to think about infrastructure, about deploying virtual machines or starting containers. That's someone else's problem. The serverless infrastructure is fully managed. Now you get an increase in the event rate. You get many events in a short period of time. Your application execution needs to scale to handle the increased workload. But you don't have to worry about scaling. You don't have to manage the state of the newly created VMs. You don't have to create those virtual machines. That's someone else's problem. The application automatically scales with the increase in load. Okay, now you have a bunch of machines that started when load was high, and they're idling, doing nothing, wasting electricity. They need to be disposed of. But you don't have to think about that. You don't have to worry about cleanup. You don't have to detect which machines are actually idle. You don't have to worry about optimizing the reuse and deployment of machines. That's someone else's problem. Function executions in serverless are ephemeral. They're automatically deleted when no longer needed. So these were the benefits of serverless. But as I said before, serverless is a triple-edged sword. So what are the limitations? Well, serverless applications are fully managed. This means that you have limited access and control over the deployment stack. You have limited access, control over, and visibility into the operating system, the language runtime, the underlying virtual machine configuration, etc. Serverless applications scale automatically. This means you have limited control over the scaling behavior, limited visibility into and control over resource use, etc. Serverless applications are ephemeral, which is perhaps the hardest of the limitations. Once an execution environment is deleted, everything that was on that machine is gone. No local state, no file system, no operating system traces and logs. Now, our goal is to ensure that an application behaves correctly. Now, what existing tools do we have? Well, the main tool we have to work with at the moment is the execution log. Every function execution stores a log of its run in a persistent cloud log service. This log is essentially std out with some additional metadata. Well, what can we do with this log? Ideally, we would like to use it to detect and diagnose problems in the execution. Because the log is std out, it only stores what we thought to write into it ahead of time. Well, therein lies our first problem. The data is usually partial and relies on manual instrumentation. Someone had to manually add a print command in the code, and if they forgot, tough, nothing you can do about that. But even if you do have everything written in the log, all you can do now is detect local correctness properties. For example, if your function had a seg fault or an area out of bounds exception. You can look at the trace of a single function run and diagnose problems there. More generally, this is a class of properties that I refer to as problems you can find using an assertion. But this is not enough. We are interested in system-wide distributed properties. Serverless application is essentially a distributed system. There are many different functions and cloud services, and they interact in complex ways. What we are interested in is correctness criteria for the entire distributed system. These are user-defined correctness properties that span multiple function executions and potentially long time scales. Consider, for example, a mailing list serverless application. The application sends emails to people who have signed up to a mailing list. Correctness property in such an application might be that emails are only sent to users who have consented to receive emails from the mailing list. But the serverless function that records user consent and the serverless function that sends emails are two different functions. What's more, these events may occur in very different times. Perhaps a user gave consent in 2019 when we were all young and happy, but the email is sent today. This is a property that requires correlating different components in a distributed system. You could not write an assert statement in either of these functions to check whether the property holds or not. Our goal in this work is to build a distributed runtime verification system for serverless applications. We want to track behavior of the application in runtime and deployment, and check that the user-defined correctness properties are not violated by the application. When we detect such a violation, we report it to the developer. Herein lies our second main challenge: taking a bunch of disjoint execution histories, one for each serverless function in the system, and merging them into one coherent history. Well, it turns out that determining the order of events and the causality of events in a distributed system is a hard problem. There are two main approaches in the literature for dealing with this problem in distributed runtime verification: vector clocks and consistent full system snapshots. Vector clocks are a data structure that holds a clock per process in the system. Those data structures are then passed around along with messages from one process to the other. Consistent full system snapshots are algorithms that construct a consistent global state of the entire system by communicating the local state of each process to all other processes. As many of you will have figured out by now, neither of these is a very good solution for serverless. In a serverless applications, we have an unbounded number of processes. Every time an event occurs in the world, a new process may be started, and processes may and do die arbitrarily when idle. An unbounded number of properties makes vector clocks unfeasible, and the fact that we cannot stop new processes from being created once a snapshot algorithm starts means that snapshot algorithms also cannot work. Additionally, processes do not typically communicate with one another, so passing messages is impractical. Finally, serverless applications typically use cloud services, which cannot be easily amended to store and propagate vector clocks or produce snapshots of their local state. We wanted to work with existing systems and applications, so we needed a solution that works within these limitations. So let's summarize the challenges that we face when we're trying to do distributed runtime verification of serverless applications. The first is the challenge of instrumentation. We can't rely on manual STD outprints. It's impractical and error-prone. The second challenge is that of building one consistent execution history for the entire distributed system, without relying on vector clocks or consistent snapshot algorithms. I'll start with our approach to instrumentation. Our key observation is that recording the external interactions of a function is sufficient in a serverless application. Since function executions are ephemeral, everything that the function only stores locally can be deleted at any time. This means that anything that the function did not store in an external database or sent to the user is essentially a tree falling in the forest. It is as though it never occurred at all. This means that we can focus our instrumentation effort on the mechanisms serverless functions use to communicate with the outside world. This is typically done using SDKs, such as the AWS SDK, and other popular libraries. And because these SDKs are used across the industry, this instrumentation is reusable across applications. Indeed, while developing Watchtower, we have instrumented the AWS SDK and several other libraries. This instrumentation can be reused by anyone running Watchtower. Next, our approach to synchronizing a distributed history. Here we choose a solution that might seem surprising to some of you: wall clock. That is, the local clock maintained by the processes. At this point, some of you may be saying to yourself, didn't they teach us in undergrad physics that Einstein said you can't synchronize clocks across a distance? Well, you're right. You can't really do it precisely. But here comes our second key observation. The external services and communication used in serverless are usually multi-millisecond operations. Writing to a cloud database or sending a response to the user over a wide area network takes time, and we know that NTP can give us millisecond level accuracy within data centers. Well, the solution is not perfect. We may still get events that we cannot determine the order in which they occur. In fact, we choose a conservative mistake window of 10 milliseconds, within which we treat event order as undeterminable. In these cases, we simply consider all possible event orders when we check for correctness violations. This decision comes with a drawback though. The resulting system is sound, but it is not complete. By sound, we mean that if we did not detect any property violations, then we have a guarantee that the application worked correctly. But it is not complete, meaning that if there was a report of a violation, it may be a false alarm. It is worth noting that in our case studies, we did not encounter any cases of events that we could not order. We've combined all this in a system we call Watchtower. Watchtower uses serverless functions to guarantee that it scales along with the application we're verifying. Also, importantly, we performed the property checking out of band, so that we minimize the user-perceived latency, which is important for interactive applications, at the expense of delayed notification of violations. Well, property violations are reported, on average, 10 seconds after the violation occurs. The user-perceived overhead of Watchtower is between 2 and 25 milliseconds on average, depending on the application and workload. A compute overhead added by running Watchtower is 125 milliseconds of Lambda compute per application request. There's a whole lot more in the paper that I haven't had a chance to discuss in this video. Watchtower supports adding properties while the application is deployed, and checking whether they were ever violated in the past. Additionally, we have a record and replay debugger. It lets you recreate the state of the system at any point in the past and investigate the execution using your favorite step-by-step debugger. There's also a detailed performance breakdown, technical details of the implementation, as well as case studies and example properties. To summarize, I presented Watchtower, a runtime verification system for serverless applications. Watchtower uses wall clock to synchronize the distributed system, albeit at the expense of a loss of completeness. It has a simplified and structured instrumentation mechanism focused on reusable instrumentation of SDKs and libraries, and it uses serverless to achieve the same scaling behavior of the underlying application. And finally, I'm on the job market, so let's talk.